Okay, so if you can see the front of the classroom, this is one of the systems that we will be studying toward in the second half of this semester. Now, it's just a simple system. You have a spinning disk, nothing electronic, no devices, no power. The only thing is that you have this massive spinning disk inside. And you just put it to a support so that it doesn't slide. The only thing that this support does is it prevents it from sliding. Not so effective. It slowed down a bit. Okay, so it has to get faster. Now, if you have a bicycle, you can do the same thing. I mean, you don't need to have such a fast spinning object. Just remove the wheel from your bicycle. I will try to bring a bicycle wheel to the next class. Remove it from the bicycle. Okay, so probably it's now fast enough. So you had already seen that the thing that the support doesn't prevent it from falling down. But if it is spinning fast enough, it will not fall down. It will just rotate. Now, just take your bike, remove the wheel from your bike, and hold it with both your hands, and just rotate the wheel. And once it starts rotating, just remove one of your hands so that it will just stay on one hand only. So just try. Try to hang that one hand that you are holding on a string and see if it will fall down or not. Okay, thank you. Now we will create a slightly modified version of it now, and you can play it during the break. This is Vedat, by the way. You will probably meet him in the department quite often. And he will just leave it, so in the break you can play with it. Well, here are your quizzes also from last lecture, so you can pick up your quizzes also if you want in the break. I mean, I don't want to keep your quizzes, so if you don't take it, I will probably just throw it away. I already gave you your grades, so have a look. I mean, there's nothing much written on the quizzes, just your grade. But if you want to keep it, just take it. Now, one thing about your quizzes, and one thing that I'm trying to stress quite often, whenever you write something, think about what it means. That's important. This way you will also catch your mistakes or which parts you are not really understanding, so you can review them. Now, if you remember the quiz question, we had this vector A, which was 3 meters x hat plus 2 meters y hat. Well, this was the question. Probably the numbers were different. 3 meters, 2 meters, and you were required to write this one, the vector. You see, a vector carries two information, that is the magnitude and direction. So if you write something, write a vector and give it to your friend. He should understand what is the direction of that vector, what is the magnitude of that vector. So you will not be going around explaining what your expressions mean. So it has to be clearly written on what you write. Now, some of you just wrote, okay, this is the A is equal to square root of 2 squared plus 3 squared. This is equal to square root of 30. Okay, this is a number. It doesn't have any direction information. There were some of you who wrote A is equal to square root of 6x hat y hat. It's not just a single person, by the way. I mean, there were several people who wrote such things. So the problem is, what does this mean? Does it carry a direction information? What is the direction of this expression? This one. By the way, there is such a symbol, x hat, y hat. There are such expressions which you will probably not meet until your graduate studies. These are called dyadics. And that's definitely not the answer to the question. So what does this mean? If you just ask yourself what is the meaning of what you have written down, then you would see that what you write down doesn't really make any sense. Now, this holds when you are solving a homework question to be handed in, or solving a exam question, again, to be handed in. You should also pay attention to how you write things when you are studying on your own, not just for things that you are handing in. So when you are studying on your own, you should solve questions, many questions on your own, not just the homework questions. When you are solving them, just at every step, at every line you write, does that have a meaning? If you hand it to your friend, will he understand what you mean? If your answer is no, then you're not writing it properly. This holds for unit, this holds for vector science, this holds for whatever you can think of. Okay, any questions about what we had been discussing on Tuesday? If you remember, we were talking about mainly two things. We were discussing the projectile motion and we were reviewing the circular motion. Okay. Now let us, one thing that we have to do this year at least is that we have to precisely define the tools that we are using. Now, one of the tools that we will be using will be reference frames. What are the reference frames? Now, we have been talking about the position of objects and the position of an object at a certain time. Now, whenever we are talking about the position and the time, we are assuming that we can measure the position of an object at every time. We can measure the time and we can also measure the position of the object at every time. Now, reference frames are mathematical tools, are inventions that tell us that we can actually do this thing. Now, how we do this? This is just imaginary construction. We imagine, let's just do a two-dimensional example. This is the x, this is the y, this is our reference point. And at every point on the x-axis, you just imagine you draw a perpendicular line. At every point, not just a finite number of them. And you also do the same thing for the y-axis. At every point you imagine that you draw a horizontal line, a line parallel to the x-axis. So that if something happens, let's say at this point, you know which lines are intersecting that point. So in principle, at least, you can determine its position. So this allows us to determine the position of a system. Secondly, what we do is we just put some clocks at every point. These are just hypothetical clocks. So we put a clock over here, another clock over here. Of course, they should all be showing the same time at the same, they should be showing the same time at the same time. So again, we have these clocks everywhere. They have to be synchronized. And so that, we have all these clocks, all these intersection points. So if something happens, let's say here at a given time, we can determine its position, we can determine its time. So it seems simple, but the underlying physics, one of the things that led to special theory of relativity was just this construction. We are assuming that the clocks can be synchronized. Can they be synchronized? If you say yes, we are in Newtonian physics. If you say no, we are in special relativity. Now, this whole construction is what we call a reference frame. So whenever we talk about reference frames, we will be imagining some coordinate axis and watches in that, moving with that coordinate axis. So that will be our definition of the reference frame. Now, one question, where is this reference point? Where do you put that reference point? For example, just give me an example. Where is the origin? I mean, we are trying to describe the physical world. So where is the origin? Wherever we want. Wherever we want, okay. Where would you like to decide it? Put it? What is x, what is y? How do you choose that? Yeah, you see, you first choose which point they intersect. Then you draw the x and the y axis. So just choose one point. Okay, over here. Fine. This is one reference point. X axis, y axis. Somebody else who wants to choose some other reference point? Okay, over there. You are the reference point, okay. I am the reference point. Okay, so do you agree that all of these are valid?
You have to be stable.
Do I have to be stable? What does stable mean?
All stable.
Stationary, what do you mean by stationary?
Not moving.
Not moving relative to which reference point?
Relative to that reference.
Why did you choose that reference point to define your stationary?
Because you were initially there at time 0 when you said you were the reference point.
Okay, what makes me special? What makes that time t equals to 0 special?
Nothing.
Nothing. So why that? Somebody else maybe defines me as the stationary. Then none of the other reference points are valid. They're all moving. Okay, so that is one thing, the relative motion. But you see, if you want to talk about motion, you have to be able to make distance measurements. You have to be able to make time measurements. To do those measurements, you have to construct a reference frame. That is arbitrary. So it doesn't, well, you say stationary, but stationary again refers to motion. And if you want to refer to motion, first you have to choose a reference frame. So where do you start? You cannot use, before choosing one reference frame, you cannot talk about being stationary, being in motion, or etc. But that also means that since the distances, let's do an example. Suppose that I am, your friend is over there. Let me just show his reference frame, one-dimensional reference frame for simplicity here. I am another reference frame. X, let me just denote this by x prime. I have these two reference frames, so that's basically, I can determine the position of an object, the change in the position of an object, and measure the time that things happen in both of these reference frames. But of course, your friend can look at me, and he can tell me that I am moving relative to his reference frame. So, because if this is t equal to 0, let's say, at a later time, this will be, let's say, here, and this will be here. This is time t, non-zero. This distance, let's just call it delta x. So he would tell me that I have moved by delta x in this time. So my velocity, according to him, will be just delta x over t. Let me just call this one O, this one O prime. So the velocity of O prime with respect to O will be just delta x over t. Of course, I am moving, this is the velocity of this point. This is the velocity of this point O prime, according to him. The velocity of that point relative to O prime is just 0. So there is one measurement that says that this point is stationary. There is another measurement that says that this point is moving. So being stationary is just arbitrary. Natural laws cannot depend on the concept of being stationary, because we want to write down laws, or we want to formulate our understanding of nature that can be used by anybody, not just one special person. So one person can choose this reference frame, the other one can choose this reference frame, and according to these two reference frames, the velocities might be different. Now let's generalize all this thing to 3 dimensions. Or on the screen it will be just 2 dimensions. Let's say this is x-axis, this is y-axis. This is a reference point O of this reference system. O prime is the reference point of the other reference system. This is x prime, this is y prime. Suppose, now in the previous example, he was observing me. But we can both be looking at him and try to understand what is his motion. I will measure my distances. I can determine his position vector. I can just measure according to my coordinate axis, measure how much I should move in each one of these coordinate axes so that I will go to reach his point. And so I will tell that this is his position at a given time. He will also look at him. Of course, according to him, his position will be different. In my reference frame, his position, I can show it by this vector. In his reference frame, he should show his position by this vector. His position vector will be completely different. And in this case, it will be this one. And let's also show my position according to him as the capital R. Now, although the position vectors that we use, him and me, they will be different, they are still related to each other. And the relation, you can just read it from here. You see this, if you add this capital R vector and this R prime vector, then you go from this point to that point, but that is nothing but the position vector according to him. This should be satisfied at all times. So if you know his position relative to my reference frame and my position relative to his reference frame, you can just determine his position according to his reference frame by just adding these 2 position vectors. Is this clear? There's an assumption we made here. Can you identify what is our assumption?
No, we learned the reference frames and also identify. My question relative reference frames, it is also changeable. And you are guessing it is true, but at the same time, 2 relative. Which one is the true? We are calculating to something, and we already know some results, and we are saying this is the real. But at the same time, we have a relative. So, what is the truth?
Both of them are the truth. You see, it's the description of the same thing, but from different perspectives. You see, you can say it like this. I see something like 100 faces here. You look and you just see, I don't know, 4 back of heads. They are the same thing. They are both true. And you see 1 face. They are both true. Although we see different things, we see different aspects of the same truth. Here also, the position, you see, these mathematical objects are our inventions. Where is his position? According to him and according to me, he is right over here. This is the truth. We of course represent it in different ways. And whenever we are writing down, we are trying to formulate the laws of physics, we have to make sure that the laws that we write should be valid no matter how we represent the physical reality.
From previous page, I didn't understand the velocity of all primes, all prime.
Well, you see, let's see. To determine the velocity of object, well, these are average velocities. To determine the velocities, what do you do? You measure the displacement. Okay. So you measure the first position of an object. Well, in this case, we want to measure the position of O prime relative to O prime.
First O prime.
If we want to determine the velocity of this point in this bottom reference frame, what we should do is we should first determine the position relative to this reference frame, and then at the successive moment, we should determine the position again with respect to this reference frame, take the difference, that is our displacement. So what is the position of O prime in this reference frame? 0. What is the position of this O prime relative to this reference frame? So the O prime relative to this bottom reference frame didn't move. If it didn't move, it means its velocity is 0. How many of you have ever taken a train? You should try, take one. And try one thing. You just sit in the train, and when the train starts to move relative to Earth, for an instant you will just, if you can ignore the vibrations of the train, you will see that all the people outside started to move backwards. It's the same thing over here. Now, in daily life, when we say that something is stationary, well, this already tells us that if you want to talk about motion, you have to always specify a reference frame. In daily life, we don't. We say that, okay, the car is going by 60 kilometers per hour, or your friend is stationary, he's not moving. When I'm walking, you say that, okay, the professor is moving. That's because we always implicitly assume a reference frame fixed on Earth. So in daily life, we always assume that we are talking relative to that reference frame, fixed on Earth, on the surface of the Earth. But in physics, when you need to be precise, you always have to specify your reference frame. Which reference frame are you talking about? Question?
If there is nothing in our environment, and if we are in entirely space, we do not understand whether we are moving or not. But the acceleration is 0.
If acceleration is 0. Now we will come to that in a moment. What your friend is basically stating, if you let me repeat it, well, you see the velocity of an object relative to itself is always 0, no matter what. So if you are in empty space, you won't be accelerating, so there's no way you can tell your velocity relative to, let's say, Earth. So you will not be able to tell whether you are moving or not. Well, now we have actually seen that if you don't specify a reference frame, even talking about motion doesn't make sense. You first have to be able to specify some reference frame. Now let's come back to this simple looking relation. There is one important assumption we made here when we are writing this relation. Can anybody figure that out?
Points are not moving or moving at the same speed in the same direction.
No. I mean the points are independent of the reference frame anyway.
They're the same sequence.
No. I mean this is valid even if we are in 3 dimensions. It's just not easy to draw it on this screen.
Monitor which reference frame you use, the laws of physics are different.
So how should I modify it if that is not the case? Okay, you are getting close though.
Axes are parallel. Axes are parallel.
You don't have to take the axis to be parallel. Of course, then you have to be careful about how you add these vectors in terms of components, but that's just a mathematical difficulty.
Y is upward when the first direction y, first direction is x.
No, I didn't say that this direction is upward on the screen. This can be in space, in empty space where there is no up or down.
Their scales must be same.
What do you mean?
Their scales, like,
The reference frames are infinite.
their scales, like, units must be same.
Well, that's always the case. I mean, if you want to write any mathematical expression, any mathematical sum, the units always have to be the same.
Velocity is constant?
No, not necessarily. I mean, this will be true even if the velocities are not constant. Let's see. When you determine this vector r, what do you do? How do you determine this vector r? That is the position, let's say his position relative to his reference frame. What do you do? Sorry? No, I mean it's not a problem of which direction r prime is. But let's say I will ask two questions. One is, how do you determine r in real life? I mean, this is the example. This is our reference point, and you want to determine this vector r. You choose your axis, and the position you want to determine is his position. So how do you determine the components of r in real life? Measure. Yes, you make measurements. You measure distances. You measure distances in this reference frame. Okay, r prime, if you want to determine his position relative to my reference frame, you make, again, measurements, but this time with this reference frame. So you have these two measurements in two different reference frames. How do you know that they should be equal? So here what you are doing is this r vector is a measurement that I should do in all reference frames. But this r prime is a measurement that I have done in the O prime reference frame.
I tried to say that.
Yeah, I mean, you were also close. But it's not a problem of units. You can use the same units. Nevertheless, even if you use the same units, how do you know that the distance measurements in two different reference frames will be the same? You can prepare these two reference frames identically. And then, I mean, we can just go there, take two rulers, compare our rulers, see that they are identical, and then I just start moving relative to you. So we are using the same units, but nevertheless we are two different reference frames. How do we know that the two measurements in two different reference frames are the same?
Changing the position must be the same for the...
Okay, we will look at the motion now. I mean, we will be looking at the change in the positions of this point, etc. now. But even before that, we don't really know that the distance measurements in two different reference frames have to be the same. In fact, now we know that it's not true. If you measure distances in two different reference frames, if they have some relative velocity, then the distances measured will be different. And that would just lead you to special theory of relativity. Just such a, if you just realize what is wrong with, what is your basic assumption and what can go wrong with your this basic assumption in writing this, you could have discovered special theory of relativity. Okay, so any questions on this one?
If dimensions of reference frames were different, for example, O would be 2 dimensional, O prime would be 3 dimensional.
I mean, you see, the reference frames are just our mathematical tools that we use to describe the nature around us. So it's not, I mean, if your nature is three-dimensional and that's what we observe, you will not use three-dimensional reference frames. You will not be able to describe what you see around you. You will not be able to describe the actual universe.
So we can't take the reference point of two different dimensions.
No. I mean, the dimension is not a property of the reference frame. It's a property of nature. So if the nature is three-dimensional, whichever reference frame you want to use, if you want to be able to describe the position of every point in the universe, you have to use three-dimensional, three-axis. Okay, so let me just call these ones R0. So initially, this is the position of this object at the O reference frame. This is the position of the O prime reference frame relative to the O reference frame. And R0 prime is the position of this point, position vector of that point relative to this O prime reference frame. At a later time, now our object might move somewhere over here. Then of course R0 will become, let's say, R1. This is at time t equal to t0. The reference points, they can move relative to each other. This is R1. And of course, since this point is moving, this reference frame is moving. So R0 prime will also become R1 prime. And this should also hold. This is at time t is equal to t1. Well, you can just look at the differences. Just subtract this first line from the second line, and that will tell you that the change in R, small r, is equal to the change in capital R plus the change in small r prime. This should also hold at any time. Not necessary. Not necessarily at time t0 and t1. Okay, so the bird is down. Okay, so this should hold. Well, we can just divide both sides by the same time, delta t. But you see, this is nothing but the velocity of the object relative to O prime, O. Let's just show it by small v. This is the velocity of the O prime reference point relative to the O reference point. Let us show it by capital V. And this is nothing but the velocity of my point relative to the O prime reference frame. And let us denote it by V prime. So you see that the velocities measured in different reference frames will be different. And we can just do the same thing for accelerations, for the changes in the velocity. So if this holds, then the change in V should be equal to the change in capital V plus the change in small v prime. And the trick is again the same, divide by delta t. And we have the relation between the accelerations measured in different reference frames. So you see, the reference frames can even have an acceleration relative to each other. There is nothing that would prevent it. You are completely free to choose your reference frame. So if you choose one reference frame, your friend chooses another reference frame. The velocities that you measure, that you two will measure, they will differ. But although you are describing the same physical phenomena, the way you represent them will be different. You will be measuring two different velocities, and you will, if you are accelerating relative to each other, you will even measure different accelerations. And although you obtain different velocities and different accelerations, you will be both correct, describing the same physical phenomena, his motion. What's your name, by the way? Ur. We will be describing the motion of Ur. And we will both be correct. Even we have different expressions for the velocities, different expressions for the accelerations, we will both be correct. So this also tells us one more thing. If you just tell me the velocity of an object, it doesn't have any meaning. I will not be able to tell the motion because you are not telling me which reference frame are you studying the object. So the velocity without specifying a reference frame or acceleration without specifying a reference frame doesn't have any meaning. So if you want to be precise on what you have, what you want to tell just imagine you are writing down and sending it to your friend. If you just write a velocity, your friend will have no idea what the actual motion of your friend is, of the object is, because you are not telling him the reference frame. Okay, any questions up to here? Okay, there are a few things that I don't like in the book. This is one of them. Acceleration, the accelerations measured in two reference frames will be the same only if the two reference frames are not accelerating relative to each other. So this is what we obtain here. If A is 0, in that case, the two accelerations are the same. A0 meaning V, the relative velocity of the reference frame is constant. Unless this is satisfied, the accelerations will not be the same. Any other questions? So now, if the accelerations can be different in different reference frames, well, there is not much hope that we can come up with a single formulation that would tell us what the acceleration of an object is in any reference frame. So what we actually do is we don't study the nature in an arbitrary reference frame, unless you are doing general relativity, but we pick up a special kind of reference frame, what we call the inertial reference frame. Okay, what's an inertial reference frame? So does anybody know what an inertial reference frame is?
Is this about Petri reference? Is this about Petri reference?
No. Okay, let's define it. Okay, this is one possible explanation for the Newton's first law. In an inertial reference frame, an isolated object, we can think of this as an object that feels zero net force. We didn't yet define the force, that's why I try to avoid this expression in the parentheses, but you can also put it over there. Keeps its state of motion, meaning that if it is at rest, it will stay at rest. If it is moving, it will keep moving at constant velocity. This is what's called Newton's first law. Now, this is also a definition of an inertial reference frame. So most of the time, in most places, you can see that the definition of an inertial reference frame as a reference frame that moves at constant velocity. That is, acceleration is 0. Acceleration is 0. Now, but if you want to talk about velocity, you first have to choose one reference frame. So, an inertial reference frame is a reference frame that moves at constant velocity relative to which reference frame? So that's not really a definition of a reference frame. This is the definition of a reference frame also. Now, how is it a definition? Well, we always say that physics is an experimental science. So at least in principle, you should be able to measure what you are defining. So how can you measure whether an inertial reference frame, whether a reference frame you have is inertial or not? Here is the answer. You take one reference frame. On that reference frame, just take some object, isolate it, just make sure that there is no net force acting on it. If it keeps its state of motion, then we know that it's an inertial reference frame. So that's how we define the inertial reference frames. Once you know one inertial reference frame, you know infinitely many inertial reference frames, because any other reference frame that has 0 acceleration relative to your first determined inertial reference frame will also be an inertial reference frame, because the accelerations in all inertial reference frames will be the same. This is actually what the book was trying to say. So we can determine inertial reference frame. Newton's first law first allows me to determine an inertial reference frame. And secondly, once I determine that a given reference frame is an inertial reference frame, it tells me how any object moves in that reference frame. So although I use just a single object to determine whether my reference frame is inertial or not, once I say that it is inertial, then I know that all the objects, if they are isolated, they will keep their state of motion. They will not accelerate. And the other laws of Newton's other laws will be valid only in inertial reference frames. So if you want to use the Newton's laws, you have to stick to inertial reference frames. You cannot choose any other reference frame. Any questions on this? Okay.
The planet, the inertial reference frame to us.
Well, Earth is not exactly an inertial reference frame, but it's almost an inertial reference frame, in the sense that unless you make very precise measurements, there's no way that you can see any deviation from an inertial reference frame. But there are some experiments, like, have you ever heard of Foucault pendulum? Now, if you just construct a pendulum that's like, it should be something like 4 or 5 meters high if you want to see a visible effect. A pendulum, it's just something like, you have a mass at the end of a string, and you just let it go. It just goes back and forth. In an inertial reference frame, it should always move in this plane. Just like the projectile motion, there is nothing that will cause it to curve, let's say, in an inertial reference frame. But if you build a huge pendulum, like 3-4 meters high, then throughout the day, you will see that it will make such a motion. It will not move in a plane. This is one measurement of the deviation from an inertial reference frame. In most practical applications, we will assume that the surface of the Earth is an inertial reference frame. For example, one example of we will assume that the surface of the Earth is an inertial reference frame. So if you are sitting in the car and the driver just pushes the fuel. So you see, are you in an inertial reference frame? You are sitting in the car. Let's just imagine one of the dolmushes. You took the dolmush, you are sitting there, and suddenly the driver just starts to go forward. Are you an inertial reference frame, the dolmuş?
This example exactly in the Earth, it could be eligible because the other factors could be affected. Maybe you are sitting just and you are moving on the car, and
No, this is the example I have. One of the dolmuşes over here that I'm sure you have taken. You are sitting in the dolmuş. Suddenly the driver pushes the fuel pedal. At that moment, is it an inertial reference frame? When you go out of this classroom, take the dolmuş, okay, and then, I mean, if you want to experiment it, take the dolmuş, and how will you be able to tell whether it's an inertial reference frame or not? The real one.
No, it's not.
Okay, you test it.
We do not keep our state.
Well, I keep my state
Yeah.
in the dolmuş fixed. I'm not moving. According to I'm sitting on the chair, and when the dolmuş starts to move, I will still be sitting in my chair. So my position doesn't change. I'm not accelerating.
But for example, you can shake it more towards the front of your back can be separated from the seat.
Now you see, you will be sitting like this, right, in the dolmuş. You will not be leaning forward, etc. You are just waiting for the dolmuş to leave.
Don't it move when the door stops?
Do you?
Yes.
Yeah, I mean, you do move. I mean, at least your head moves, even if your back doesn't move. So the dolmuş, yes. Yeah, no, him first.
For the people inside the dolmuş, your frame is internal reference frame, but from the outside, yours not.
Don't look outside. Now, even if you are inside, even if you are not looking outside, the reference frame of the dolmuş is not an inertial reference frame.
Because you feel the acceleration.
Yeah, how do you feel the acceleration?
When it goes forward or slows down.
Now, what will you observe that makes you feel the acceleration? Okay, from the CDs, for example, you will see that the CDs, although there is no apparent force acting on it, they will just move backwards. So there is a force. It wouldn't appear. Yeah. Or when the driver brakes also, apparently there is nothing acting on you, but suddenly in the reference frame of the dolmuş, you just go forward. So that's still not a reference frame. To determine whether a reference frame is inertial or not, you don't need to look outside. Then Newton's first law allows you to determine whether your reference frame is inertial or not. Because if you are looking outside, you are basically comparing your reference frame with another reference frame. How do you know that the other one is inertial or not?
when you're sitting on the dolmuş, force is zero or not?
We will discuss it when we discuss the Newton's second law.
If it is zero, your example is inertial.
We will discuss it in the second law. Newton's second law.
Center force.
The concept of force, I'm trying to avoid it as much as possible. Even here, I would have preferred if I had avoided it, because the force we will define. What do you mean by force? We will define it with the Newton's second law. So before defining what the force is, let's just try to keep away from discussions involving force. And hopefully once we define what force is, you will also learn whether an expansion is a force or not. Other questions before the break? Yes.
What is the right word for inertial in Turkish or in Turkish?
Not one that I know that's commonly used. What I use is eylemsiz referans sistemi. Well, one problem in Turkish is that there is no general consensus on which words to use for the technical terms in Turkish. Okay, see you after the break.